Hey everyone, Victor is here, your organic chemistry tutor, and in this video I want to go over must-know reactions of aldehydes and ketones that you are going to see in your course. This is going to be an overview video, so I'm not going to go over every single detail for every single reaction. However, by the end of this video you'll have a pretty good idea of the chemistry of aldehydes and ketones and what to expect from this chapter in your class. So first of all, what exactly is the difference between aldehydes and ketones? Both functional groups contain the carbonyl, which is a CO double bond. However, when it comes to aldehydes, they do have at least one hydrogen connected to a carbonyl. So you can remember that an aldehyde contains an H. It's sort of like an easy mnemonic that you can remember. When it comes to ketones, they are going to be connected to two carbon-containing groups. So for instance, butanol is going to be an example of an aldehyde because we have this H over here. There is one important thing I want to point out here. The hydrogen of the aldehyde, the one that used to be here a moment ago, that one can be implicit. We don't have to show it. A lot of people traditionally do show it, but we don't have to. Now, one of the important physical properties of aldehydes and ketones is the fact that the carbonyl, the CO double bond, is extremely polarized, giving us a large delta plus on the carbon and some delta minus on the oxygen. This means that our aldehydes and ketones are going to be susceptible towards reaction with nucleophiles, and the vast majority of reactions of aldehydes and ketones are going to be reactions with different nucleophiles, where we have some sort of a carrier of the electron pair making a new bond between carbon and the nucleophile, and then we get our final products depending on the nature of the reaction itself. And in this tutorial, pretty much every reaction is going to fit into this general pattern where the carbonyls are going to be reacting with some sort of a nucleophile, giving you something new. And now, when we have a basic idea of the reactivity of aldehydes and ketones, let's look at the actual reactions. And the first reaction that I want to go over is the reduction on the heterogeneous catalyst. By the heterogeneous catalyst, we typically mean something like palladium, but you can also see things like platinum or nickel, where palladium and platinum are going to be the most common ones. This is the only reaction that has nothing to do with the polarity of the carbonyl group itself. And interestingly enough, some instructors and even textbooks skip this reaction altogether. But this is a very useful reaction nonetheless, so you should know about that. Now, we have already seen the reduction on the heterogeneous catalyst before, and that was with alkenes, where we have a carbon-carbon double bond, or alkynes, where we have a carbon-carbon triple bond. The big difference here is that in case of alkenes and alkynes, this reaction typically happens at a much lower pressure than in case of the carbonyls. Carbonyls will be reduced at a much higher pressure. I said here about 100 atmospheres at the maximum, but many carbonyls can be reduced already at 20 to 30 atmospheres depending on the nature of the molecule itself. I also want to remind you real quick here that stereochemistry-wise, the hydrogenation is always going to be the syn addition, which is not particularly relevant in the case of carbonyls. However, in the case of ketones, we can have what we call a prochiral atom. So if your carbon, which is connected to oxygen and two different carbons, is going to have three different groups, by adding an extra hydrogen to that, we are going to be creating a chiral carbon. So in this case, we might very well make a pair of enantiomers, so that is going to be a racemic mixture, or, depending on the structure of the molecule, it might even be a pair of diastereomers, in the case you have already had some sort of stereochemistry in the molecule to begin with. And while most instructors are not really going to be paying too much attention on this stereochemistry here, or testing you on that, sometimes we do see questions phrased in a way that show all possible stereoisomers for the products, or if you have other stereoisomers, right, like plus enantiomer or diastereomer or something like that. So do pay attention to this reaction because it can potentially form stereoisomers. And before we move on, I want to point out one special case of hydrogenation. Generally speaking, whenever we do hydrogenation of our aldehydes or ketones, we are going to end up with the corresponding alcohol. However, if we are going to do this reaction in the case of the benzylic ketones, and the benzylic ketone is going to be the one where the carbonyl is sitting right next to an aromatic ring, well, in that case, we are are going to end up with the complete reduction down to the CH2 group. And while in theory we do have the alcohol here as an intermediate, catching that alcohol in practice ends up being basically an impossible task. So generally speaking, whenever you have a benzylic alcohol or benzylic carbonyl like an aldehyde or a ketone, we are going to end up reducing it all the way, and we won't be able to catch that alcohol in the middle. Now, moving on, I want to look at another reduction reaction. But now, instead of pure hydrogen, we are going to be using complex hydrides. Typically, the most common examples are going to be lithium aluminum hydride and sodium borohydride. This reaction, like in the previous case, going to give you an alcohol as a product. I also want to point out real quick here that when it comes to lithium aluminum hydride, that is generally a much stronger reducing agent, which is going to be irrelevant for this part of the course, but we are going to see the differences in the reactivity of lithium aluminum hydride and sodium borohydride later on in the course, especially when we start talking about reductions of carboxylic acids and their derivatives. That's where the differences are going to be super important. For right now, they both are going to do the same thing for our carbonyls. Now, mechanistically speaking, now we are moving to the territory where all our reactions are going to be different reactions with nucleophiles, where the nucleophile is going to be attacking our carbonyl. So lithium aluminum hydride or sodium borohydride is essentially a source of the nucleophilic hydride, and that hydride is going to be attacking our carbonyl. Traditionally, we are going to show that from the molecule itself, so either lithium aluminum hydride and the source of the electrons is going to be our bond, or sodium borohydride, the idea is going to be still the same. In the course of this reaction, we are going to make a negatively charged intermediate, the alkoxide, which we are going to have to protonate using the acidic workup. Since sodium borohydride is a much milder nucleophile and a much milder base, it can be used in something like methanol as a solvent. It will react with methanol very slowly, but the reaction with the carbonyl is actually going to happen faster, which means that we can use something like methanol or other alcohols as a solvent, and in the case of sodium borohydride, typically we're not going to be seeing the workup step. Lithium aluminum hydride, as I've mentioned a moment ago, is a much stronger and significantly more reactive species, so if you try to mix lithium aluminum hydride with anything even a tiny bit acidic like alcohol or water, you're looking at an explosion because it's going to immediately start producing H2, hydrogen gas. Reaction is extremely exothermic, and the heat that is evolved during this reaction ignites the hydrogen, and that ends up giving a big boom, which is definitely not what we're looking for. So with lithium aluminum hydride, we are going to have a workup step. With sodium borohydride, we're not going to have any workup. And just like in the previous case, ketones can be prochiral, so you gotta keep an eye on the chiral atoms that you may produce in this reaction, so you can potentially make a pair of enantiomers or maybe a pair of diastereomers depending on the molecule itself. The next reaction is a Wolff-Kishner reduction. This is another way of reducing aldehydes and ketones. However, unlike the reaction with complex hydrides or hydrogen, we are not going to be making an alcohol here, but rather we are going to reduce our carbonyl all the way completely to a corresponding methylene group, to a CH2 corresponding alkane. There are two ways how we are going to perform this reaction. Version 1 is what I like to call mixed conditions, where we first going to make the CN double bond, which normally we would call an imine. However, when you have another nitrogen attached to that, that one is called hydrazone. So in the first step we're forming the hydrazone, and then we're going to treat it with a base, typically potassium hydroxide, at a very high temperature, and that going to give you the final product. I'm not going to go through the mechanism here, it's very long and convoluted, and I will have a dedicated video for that, but as a result we are going to end up without a carbonyl, and that's just going to be a CH2 group here. The other conditions is where we are going to take our carbonyl compound and we are going to treat our molecule with hydrazine and base right away. So during this reaction we are still going to form the hydrazone as an intermediate, but it happens all in the single pot. Now, the problem with this reaction is that we are using an extremely high temperature, and typically we're looking at temperatures from 120 degrees all the way to 250 degrees, which means that not that many organic substances can physically tolerate conditions like that. On top of that, many organic substances have relatively low boiling points, so if you try to do this reaction, your compound will just fly away. And also, since a lot of molecules tend to pyrolyze or basically get destroyed at high temperatures, this reaction is only useful for extremely simple cases and the molecules that can tolerate extremely high temperatures, which is not that many. So while this reaction looks cool on paper, in reality we virtually never use that. What we do use, however, is the Clemmensen reduction. This is another way of completely reducing the carbonyl and get rid of the CO double bond. The difference from the Wolff-Kishner is that we are using much milder approach here, although we are working in acidic conditions. So this might be a detrimental factor for molecules that don't tolerate acids well, but you choose your evil. Either you have to tolerate high temperature and basic conditions, or you have to tolerate the acidic conditions, or there are other ways that can work, so we'll talk about that as well in a moment. Now, the cool thing about the Clemmensen reduction is that we typically do not cover the mechanism of this reaction. It involves a lot of single electron transfers and funky looking intermediates, and typically that goes beyond the scope of the course, but if you guys really want me to show the mechanism, let me know in the comments below and I can definitely make a video about that. So just remember that in most cases, if you want to get rid of your carbonyl, you are just going to be using the zinc amalgam and some sort of acid, typically hydrochloric acid, and we're in business. Now, if neither Clemmensen reduction nor Wolff-Kishner work for our purposes because maybe our molecule just doesn't tolerate either of those conditions, there is one other way how we can deal with that, and that is going to be the reduction of thioacetals. This is the last reduction method, and it again allows us to completely get rid of the oxygen. In this case, that's going to be a two-step process where first step, relatively mild conditions, we are going to convert our carbonyl into corresponding thioacetal, and then we are going to reduce it with the hydrogen, specifically on the Raney's nickel. Raney nickel is a type of a heterogeneous catalyst that has been prepared in a special way, and it works here by ripping the sulfur off and essentially putting the hydrogen instead of that. And of course, this is an extremely simplistic explanation of what happens here, but it turns out that Raney nickel works here. Other heterogeneous catalysts, they don't really work that well here. So if you want to use this reaction, you gotta remember that out of all of your heterogeneous catalysts, you gotta use this one. And as I've mentioned, the cool part about this reaction is that it is done in mild conditions. However, this reaction is incredibly stinky, and another thing that you need to keep in mind, if we are using hydrogen on heterogeneous catalysts and you have a double or a triple bond somewhere else in your molecule, you are most likely going to reduce that one as well, so you gotta keep that in mind when planning your synthesis. Now, the next reaction that we have here is probably one of the most important reactions of aldehydes and ketones, as it allows us to make new carbon-carbon bonds. Typically, we are going to do this reaction with the Grignard reagent, which is the organomagnesium compounds, or organolithium compounds, which for our purposes are pretty much the same deal. The general mechanism here is relatively straightforward, where your organometallic compound going to react with our carbonyl, so this is a nucleophile, our carbonyl is going to be an electrophile. We are, like in many previous cases, going to form a negatively charged intermediate. In this case, we have formed a new carbon-carbon bond over here, and then we're going to do the workup. The organolithium compounds, they are generally more reactive than organomagnesium compounds, but again, for the purposes of the chemistry of aldehydes and ketones, that is not particularly relevant. And like in our previous cases when we were making alcohols, if your ketone was not symmetrical to begin with, you can potentially make a new chiral carbon right over here, so that means that the molecule can end up giving you a pair of enantiomers or maybe a pair of diastereomers. Now, as I've mentioned in my dedicated video on the Grignard reaction, when it comes to organometallic compounds like the Grignard reagent or organolithium compounds, these guys are incredibly basic, which means that anything that is even a little bit acidic is going to be, well, too acidic for them. The Grignard reagent and organolithium compounds, they cannot coexist together with alcohols, thiols, carboxylic acids, amines, or even terminal alkynes. All of these functional groups are too acidic for the Grignard reagent and organolithium compounds, so if you have any of those, the acid-base reaction is going to happen faster than your nucleophilic attack, so you have to be mindful about that and either put a protecting group on your acidic hydrogens or plan your synthesis in such a way as to avoid the coexistence of the acidic group with the organometallic compounds in the same pod. Now, up to this point, all of our reactions were irreversible. However, there is a large group of reversible reactions of carbonyls, and in this section we are going to talk about the formation of acetals, thioacetals, imines, enamines, and also cyanohydrins. And the first set of reactions that I want to talk about is going to be reaction with oxygen-containing nucleophiles, such as water or alcohols. In the case of water, we are going to get a geminal diol, or we sometimes call it a hydrate. From the synthetic perspective, hydrates are not particularly useful, but it's still one of those things that you gotta keep in mind, that aldehydes and ketones can react with water in either acidic or basic conditions. What is more useful, however, is reaction with alcohols, that going to give you hemiacetal as an intermediate and acetal as the final product. This is one of the most common reactions of aldehydes and ketones that you are bound to see in your course. And first of all, hemiacetals and acetals are biologically relevant, and we see them all over the place in chemistry of carbohydrates. Second, they are the most common protecting groups that you are going to see for aldehydes and ketones. So this reaction is fairly important. But before we look at the mechanism and how that all works, I want to do a quick naming convention. When we are talking about acetals, you can also hear another term, ketal. Traditionally, acetal was the product of the aldehyde reacting with the alcohol, while ketal was the product of the ketone reacting with an alcohol. The current IUPAC rules say that the acetal is the dominant term and the ketal is the type of the acetal. So in other words, acetal is the umbrella term and you can use acetal for all of these derivatives. Of course, if your instructor insists on using a ketal, then go with that, but just so you know, the current IUPAC rules do not require the use of the ketal as a term at all. Now, when it comes to the mechanism of this reaction, this is one of the very common mechanisms that you are going to be tested on the exam, so that is definitely something that you want to know very well as the back of your hand. I am not going to go over every single detail of this mechanism for right now, I will talk about that in the dedicated video, but for right now you can see that the mechanism is fairly long and it involves a lot of acid-base chemistry and a lot of equilibrium steps. Talking of which, everything that we are going to be talking about from now on until the very end of this video is going to be an equilibrium with the exception of very last reaction. So when it comes to formation of the acetals, that is an equilibrium which is going to be guarded by the Le Chatelier principle. So if we want to force the formation of the acetal, then we are going to have to remove the coproduct that we have in this reaction, and coproduct is going to be water. So by removing water, we are going to force the formation of the acetal. However, we can take the acetal, add water, have the same acidic conditions, and that going to get all the way back to the original carbonyl and the alcohol. So you can make acetal and you can just as easily break the acetal using the Le Chatelier principle. I also want to point out that we are often going to see cyclic acetals. They are very common as protecting groups, so that is definitely something that you are going to see in your course more than once. In the case of cyclic acetals, each of those R groups that we have on our oxygen becomes a part of a one cycle, but from the chemical perspective, that is still the same deal as if there was no bond between those two R groups over here. So when you see a cyclic acetal like this one, that's no different than the regular acetal, so don't get confused or scared by that. And the product that is extremely similar to the acetals is going to be thioacetals. Thioacetals are extremely similar to acetals, but we have sulfur instead of our oxygen atoms. Importantly, due to the higher nucleophilicity of sulfur and higher stability of thioacetals, we typically do not see hemithioacetals. So looking at this mechanism, I am going to produce the hemithioacetal in the middle of this reaction, but we're never going to even talk about that because the reaction typically goes all the way to the completion, to the formation of our thioacetal. And while this reaction is reversible like in the case of the regular acetal hydrolysis, here, in order to force the hydrolysis of thioacetal, we're actually going to use the mercury 2+ that will be binding away the sulfur-containing moiety in this molecule and physically removing it from the equilibrium. Otherwise, due to a much higher nucleophilicity of sulfur compared to oxygen, the hydrolysis of thioacetal without mercury is going to be quite problematic. Now, moving on, we have nitrogen-containing nucleophiles. So when aldehydes and ketones react with ammonia or primary amines, they are going to give you an imine, which is a CN double bond. However, when we react our carbonyl with the secondary amine, the nitrogen-containing two other groups, we are going to end up with an enamine, where you have a double bond next to a nitrogen and not a carbon-nitrogen double bond. Both of those species are important intermediates in organic synthesis. Former imines, they are typically used in synthesis of various amines in synthetic sequence known as reductive amination. The latter, the enamine, they are used in making new carbon-carbon bonds in reactions like Stork-enamine synthesis and similar reactions. From the mechanistic perspective, both reactions are extremely similar to each other. We are going to start with a nucleophilic attack on our carbonyl, and the only difference is going to be at the very last step. In the case of the imine formation, we are going to have a proton sitting on our nitrogen, so we'll be able to deprotonate a positively charged nitrogen and stabilize the molecule this way. In the case of the enamine formation, this nitrogen over here does not have any protons on that, so we cannot easily stabilize it by deprotonating this molecule. So what we have to do, we have to take a proton from the nearby carbon, and that gives us a carbon-carbon double bond rather than a carbon-nitrogen double bond. Depending on the structure of your course, you might see the formation of imines and enamines in the chemistry of carbonyl compounds, or sometimes instructors choose to cover this chemistry in the chemistry of the nitrogen-containing compounds. So if you don't see that right now, don't worry, you will see this reaction in the future towards the end of your course anyways. And one other reversible reaction that I want to talk about here is the formation of cyanohydrins. This reaction has a very narrow applicability, but is generally very useful in various chain extension strategies. Mostly, this reaction is going to be used in the carbohydrate chemistry, so once you guys start talking about the sugars, you will see this reaction more than once for sure. From the mechanism perspective, this is a very simple nucleophilic attack on a carbonyl. Typically, we're going to protonate our carbonyl first, and then cyanide is going to perform the nucleophilic attack. Like previous reactions, this one is an equilibrium, so we can easily reverse it back. Typically, when it comes to the forward reaction, it is catalyzed in acidic conditions. The reverse reaction is typically catalyzed in basic conditions. And mechanism for this reaction, as you see, is fairly simple. Now, the next reaction that I want to talk about here is a rather interesting oxidation of carbonyls. The thing is, normally, when we are thinking about aldehydes and ketones, we don't really think about their oxidation. Well, maybe an aldehyde can be oxidized to a carboxylic acid. We know that one. But when it comes to ketones, we definitely don't think that a ketone is a good target for the oxidation reaction. However, ketones can be oxidized, and interestingly enough, we are going to oxidize ketones with MCPBA, metachloroperbenzoic acid, or similar reagents. We remember that normally we use this reagent in the epoxidation of alkenes, but apparently it has another interesting use. And when we use our MCPBA reagent, it can insert the oxygen in between the carbonyl and the nearby carbon of our ketone. Importantly enough, we are going to insert the oxygen between the carbonyl and the more substituted group. So we are going to say that the group migratory aptitude here goes from the tertiary alkyl group to the secondary to the primary, and the CH3 migrates as the slowest in this case. And another interesting aspect of this reaction is that this reaction preserves the stereochemistry of a carbon that we are migrating. So we had a very specific stereochemistry at the carbon over here, and if we follow through the mechanism, we can see that the stereochemistry in the final product is exactly the same, which is definitely something important that you need to keep in mind when it comes to the planning of your organic synthesis and thinking about the stereochemistry and the outcome of your overall synthesis after multiple steps. And finally, the last reaction that I want to talk about real quick here is the Wittig glyphination. It is 1979 Nobel Prize in Chemistry, so you can imagine that this reaction is kind of a big deal as well. The reaction is extremely useful for conversion of aldehydes and ketones into the corresponding alkenes. It has a huge scope and it's very tolerant of other functional groups. Mechanistically speaking, like many other reactions of aldehydes and ketones, it starts by a nucleophilic attack on our carbonyl. Then there is a little bit of a debate whether we have the beta-ene intermediate or not, because some people suggest that we are going to form the oxyphosphatone right away, and we have some experimental evidence that still suggests that the beta-ene forms as well. So which mechanism is more correct here? Well, that's a good question for a debate. In my experience, instructors choose either or, so see whatever your instructor likes to use in the classroom and go with that mechanism. As a result of this reaction, we are going to make a double bond, which can be extremely useful for organic synthesis. Interestingly enough, the stereochemistry of the double bond does seem to depend on the nature of your E-lead. If we have E-leads containing electron withdrawing groups, we call those electron withdrawing groups a stabilizing group because we kind of have a negative charge over here on our E-lead. So in the presence of electron withdrawing groups, we typically going to see the formation of the E double bond. In the case of non-stabilized phospho-E-leads, we are typically going to see the formation of the Z double bond. So as you can see, chemistry of aldehydes and ketones is a very diverse field and a very large scope of reactions. I have, or will have shortly, dedicated videos about each and every reaction in this list depending on when you are seeing this video, so make sure you check out the playlist in the description below. I know it's been a rather long video, so thank you for sticking till the very end. If you like it or learned something new today, you can show this to me by hitting the like button and leaving me a comment below. Subscribe to the channel for daily organic chemistry updates and tutorials, watch this video next, and I will see you tomorrow.